Now we're going to introduce the actual name of this topic, functions and relations. So we're going to start off with relations. Anytime you see an equation that relates x and y, that's called a relation. So for example, x squared plus y squared is equal to 1. That is represented by a circle on the Cartesian plane. That's a type of relation because you have an equation that involves both x and y, and that produces some form of relationship, algebra-wise. And then you also have y is equal to x squared, which is another type of relation. This one is represented slightly differently because you have the y on one side and then everything else on the other, which is pretty common when you have rules in VC methods and just in algebra in general. This is an exception to that rule because it's like a custom thing. It's a circle, and you can see it's a bit hard to represent it in terms of y only. So that's why we just keep it as our standard form. X squared plus y squared is equal to something, but you could easily just rearrange for y if you wanted to. Now, all of these relationships or equations between x and y, they're all considered relations, but then only a small subset of them, or a subset of them, are considered functions, okay? So a function is a specific type of relation. That's what we're going to start off with, okay? So how do we know if something is a function or not, is the real question. And functions are really important for VC methods because it's a really convenient way of representing rules, and it's really important way to represent numbers as well, as we'll see in a lot of examples and pretty much every other topic that we do in VC methods from now. Even probability, believe it or not, there are functions in probability. But we're going to start off with just the layman's way of representing or finding out if an equation or a relation is a function or not, and then we're going to go to the more formal definition after that. So we've got the two graphs here, and I've drawn the graphs of these on purpose because it's actually really easy from a graph to determine if something's a function or not, and we use something called a vertical line test. Now, just before I go through the vertical line test, if a question asks you, like let's say on a SAC or something, if a question asks you to state or give reasons why something is a function or is not a function, you can't use the vertical line test because it's more of a way of just seeing for our reference. It's not an actual definition of what a function is, but a vertical line test is a really easy way of seeing if if an equation is actually a function or not. So how the vertical line test works is if I can draw a vertical line anywhere and you have more than one intersection on any instant, then it's not a function. So for example, you have an intersection there, an intersection there, so straight away we know that this is not a function, okay? So if those two intersections occur anywhere, then you don't have a function, okay? So it occurs there, and it also occurs there. It doesn't occur here, right on the edge, it just has one, but if there's any position where you have more than one intersection, then you say that it's not a function straight away, okay? Now, if we try that on the parabola, let's see with a few examples. So draw a line there, you're gonna have one intersection, you draw a line there, you're gonna have one intersection, you draw a line there, you're gonna have one intersection, and I don't have to keep drawing lines. You can see that if I draw a vertical line anywhere along this parabola, then you would never have two intersections, you have at most one. That's really important to note, at most one. You can have zero intersections in some places, that's perfectly fine, but you just can't have more than one intersection in any given place. So this one fulfills that rule, so we say that this one is definitely a function, okay? Now, what's the significance behind having this as a function? So the main significance, and you might have seen it in previous topics or previous exercises as well, and I might have even wrote it in some places. Instead of saying y is equal to x squared, you can say f of x is equal to x squared, okay? Now you might think, okay, I'm just writing more letters. Doesn't make that much of a difference to me. But it's actually really important that we write f of x is equal to x squared because it's actually a way of signifying, and this is the proper definition for a function, that if you have an x value, you only have one possible y value for that x value, okay? So I'm just gonna say that again. If you have any given x value, you should have at most one y value for that corresponding x value. Okay, and the reason why that's important is because you can kind of think of this function as like an input-output machine. Okay, it's kind of a weird way of looking at this rule, but we could kind of think about it as an input-output machine. So we have going in as the input x. So let's say x is equal to 2. Okay, so let's say, as an example, x is equal to 2. Now we put that into our function, and our function is our rule. Okay, so we have f of x here, In this case, it's x squared. So our function process, we can kind of think of it as, is the squaring of our number. So we have 2, we square that, so we get 2 squared, which is equal to 4. Now, that returns the output, okay? So the output is y, which is obviously just equal to 4. So that's the output of our process. Now, if you didn't have a function, the problem would be that you have more than one output for one input. So you don't have a predictable process, which is actually a problem. Okay, so for example, if you have the circle here, let's say this vertical line here in the middle is that x is equal to 1/2. You have multiple y values that you don't know. You don't know what the input and the output correspondence is. So that's why this can't be considered a function, because it's not that. The way of thinking about it is that it's not that proper process that we actually want for a function, or the right logic that we want for a function. So that's how I like to think about it. Now you can have no output for an input, that's fine. So for example, if you had y is equal to 1 over x, y is equal to 1 over x, and your input was x is equal to 0, you wouldn't have an output because that goes beyond the domain, because the domain doesn't allow for x is equal to 0. But that's fine as well. This can still be considered a function because it passes the vertical line test. But if we want to, maybe I should write it down so you guys actually have a written version of it. So if you ever asked to state why a function is a function or not, you say, for a function to exist, there can be, hopefully this is big enough to see on that camera, for a function to exist, there can be at most one y value for any given x value. I'm really hoping that that is visible, but I'll zoom it in on the edit. I'll remind myself by saying that. So just a quote to define, so this is the official definition, or the official reason why a rule can be a function. For a function to exist, there can be at most one y value for any given x value, and it has to apply to all x values. So this is the proper definition for why a relation would be a function. So you can see for a parabola, if you had any given x value, you would always have at most one corresponding y value as the output of our function. Now, when we define functions, sometimes in questions, they might ask us to define it using something called functional notation, or a question might define a function using functional notation. It's not very common, but it's still important to understand, how to actually write functional notation. Now, only define a function using functional notation if it actually specifies, okay? If it specifies with functional notation. If it just says define a function, I guess there is some debate about whether you should do functional notation or not. Personally, I don't. If a question says to define a function for, let's say, a modeling problem, so an application problem, I would just state the rule of the function, and I'd also state the domain as well to be safe. The implied domain / restricted domain, depending on what the question calls for. I personally don't do functional notation, but you could do it either way and you'll probably get the marks. Now, let's say if we want to define this using functional notation. So we have f of x is equal to x squared is the rule for our function. So that's an important thing to note. This is just the simple rule, and this is what we're used to dealing with up until now. And then we have a domain as well, which we have to get from the graph. And this is actually the recycled example from before. So the domain would be -2 exclusive all the way up to infinity. Now, how we define functional notation is like this. We start off with the function rule. So we have f, and we just leave it as f, just like the letter of our function. And we say such that, or colon. Such that colon is the same thing in terms of algebra. So we say f such that. And then we write down our domain. I'm actually going to use different colors for each of these things. I have enough colors here. So I'm just going to use different colors for each of these things just so we can note down the difference. So the first one is f such that. It's just the name of our function. Then we specify what our domain is. So in this case, we have -2 to infinity. And we use interval notation when we use this process. And then we have arrow r. Okay, now I'm just going to explain what this means. We have the domain here, which is pretty self-explanatory, but then we have arrow r. This is just saying that the domain maps on to the real number line. Okay, now if you ever have a function like a graph and it's continuous, it's always going to map onto the real number line, because you can see that it's just continuously in between -2 and infinity. Now, I've never seen this, but hypothetically, if you mapped it on to the natural numbers, then our graph would look something like this, where it's just the dots. right, in the same shape. Now, the reason why it's the dots is because you're mapping that domain onto natural numbers, which is just whole numbers. So that's why that doesn't really work for our continuous graphs. Continuous graphs are always just the real numbers. So that's why we just define it using the real numbers. So how I read this is -2 to infinity, which is our domain, maps onto the real number line. Then after that, we have comma, and then we have our function rule, and that's using f of x. So we say f of x is equal to x squared, okay? So we have the function handle, or the function name. We have the domain, maps onto R, and then we have the function rule there, and this is how we define a function using functional notation.